Welcome to this video on the greatest common divisor. Assume we have two natural numbers a and b. If a can be exactly divided by b, b is a divisor of a. Divisors of a natural number are all natural numbers that may be multiplied by another integer to produce the original number. For example, divisors of 18 are 1, 2, 3, 6, 9, and 18. These numbers consist of a divisor set, while divisors of 12 are 1, 2, 3, 4, 6, and 12, also forming a divisor set. Common divisors of two natural numbers include intersection numbers found in both divisor sets. For the divisor sets 1, 2, 3, 6, 9, 18 and 1, 2, 3, 4, 6, 12, the intersection numbers are 1, 2, 3, and 6. These four numbers are the common divisors, as they both can divide exactly 18 and 12. In the common divisor set, 6 is the largest number, so we can say 6 is the greatest common divisor. This is how we determine the greatest common divisor. The preceding operation helps us calculate the greatest common divisor of any two numbers. We calculate the divisor set first, then perform intersection on the sets, from which with the greatest common divisor, which is the largest number. This is a little time-consuming. To manually calculate the greatest common divisor of 18 and 12, observe the form of these two numbers first. Observation is a common means for humans to do calculations, and is the starting point to think. But since everyone thinks differently, we must prioritize intuition, because 18 can't be divided by 12. 12 is not a divisor of 18. Remember, 18 and 12 are small and even numbers. We know instinctively that 2 is one common divisor, and likewise, we know both 18 and 12 can be exactly divided by 3, making it another common divisor. But 3 is larger than 2. We can rule 2 out as the largest number. Continuing to use 4, 5, 6, 7, and 8 to divide 18 and 12, we find 6 is the greatest common divisor. We can try with 7, 8, 9, 10, and 11, but these can't divide 18 and 12. So that's our result. 6 is the greatest common divisor. The description of the calculating process is simple, but this process can be considered as an algorithm. To describe the preceding calculating process in a standard form, we can use one word, traversal. But what is traversal? Traversal is a process to traverse all natural numbers from 1 to the smaller one of two target number. We test natural numbers such as 1, 2, 3, 4, and 5 to check whether the two numbers can be divided. If a natural number can divide them, it is recorded. This number can then be considered a common divisor. Record each common divisor found and repeat this process. After the traversal, the last recorded number is the greatest common divisor. This process, compared with manual calculating, is relatively standard. It is a superior method, but might also be ambiguous and be misunderstood. Well, that's why we are here. To describe such a mathematical problem, some mathematical symbols are introduced for a clear and detailed description. The aforementioned problem can be presented in a more mathematical way. We use x and y to present two natural numbers. The smaller one is represented as min xy and can be seen as an operator. Then let's calculate the smallest value of x and y. Assume there is k belongs to the closed interval 1 min xy. We test k from the smallest value to the largest value to check whether it can divide x and y. If x and y can be divided by k, record k. After the traversal, the last recorded k is the greatest common divisor of x and y. Here, we introduced the mathematical symbols xyk, min xy, belong to and close intervals to make it easier to read. The language of mathematics is actually an extension of natural language. Math expresses problems and solutions with concision and precision, letting us use more specific words to express the logic of traversing in sequence. Assume there are natural numbers in the range of 1 min xy. If x and y can be divided by k, k is a common divisor of x and y. After the traversing ends, the last k that can divide x and y is the greatest common divisor. Let's use this algorithm to calculate the greatest common divisor of 36 and 24. This calculation can also be expressed in Python. Here we have an example of code used for traversal. Once executed, the code helps us find the greatest common divisor of 36 and 24. During the calculation, all possibilities are listed and tested. The process is called enumeration. An enumeration algorithm requires all numbers in 1 min xy to be traversed, no matter the common divisor is 1 or the smaller number of the two target numbers. If min xy is a large number, enumeration will take a long time. For 36 and 24, traversal of 24 numbers doesn't take time, but consider a number consisting of 15 or more digits. Naturally, traversal takes a long time. An algorithm can be used to accelerate this calculation. We can see or observe the preceding algorithm traverses numbers from 1. If one number that can divide 36 and 24 is found, the traversing process does not stop. 36 and 24 can be divided by 1, 2, and 3. Can they be divided by 4? Yes. How about 5? No. But the point is, the process doesn't stop, because we don't know whether they can be divided by other numbers. Let's start the traversing from larger number to 1, and determine if 36 and 24 can be divided by 24, 23, or 22. In this way, when we find the first number that can divide the two numbers, we can stop, because there's no number larger to divide them. If there is another number that can divide the two numbers, logically it must be smaller than the first found number. By doing so, we construct an array in a reverse order. The traversing starts from min xy, then min xy minus 1, min xy minus 2, min xy minus 3, before reaching the lowest value 1. The first k that can divide x and y is the greatest common divisor. Typically, the greatest common divisor is a large number, so it makes more sense to start traversal from large numbers, as this prevents us from traversing the whole dataset. which would be a much slower process. Let's use this method to calculate the greatest common divisor of 36 and 24. You may wonder if this is the best way. During the enumeration in reverse order, if x can be divided by y or y can be divided by x, the result can be obtained after one round of traversing. This is an ideal situation. If 1 is the only common divisor of x and y, all natural numbers in 1 min xy need to be traversed, and the number of enumerations is equal to min xy. But in most cases, the number of enumerations is between 1 and min xy. To evaluate the performance of an algorithm, we need to consider the number of repeated steps, or the number of calculations, especially the number of steps to be repeated in the worst case. If an algorithm calculates numbers from a small number, the number of steps is equal to min xy. But if the algorithm starts calculating from a large number, and x and y can be divided by each other, traversal is complete in just one round. Easy, right? Well, no. In the worst case, x and y can only be divided by 1, and the number of steps is min xy. These two algorithms actually have the same performance. The number of calculation operations correlates linearly to data size. The larger the data, the more operations are needed. If you are thinking there's a better method, then you are on the right track. When we think about calculation, we usually try with concrete values and then abstract values. Take an example of 16 and 6. 16 can't be divided by 6, as then we can try to calculate 16 divided by 6 and obtain 4. 6 can't be divided by 4, but 6 divided by 4 is 2, and 4 can be divided by 2. So 2 is the greatest common divisor of 16 and 6. This method is called division algorithm. It calculates the remainder of two numbers. If the two numbers can be exactly divided by the smaller one, the smaller number is the greatest common divisor. Otherwise, we continue to divide the divisor and remainder until we get the greatest common divisor. This is how the division algorithm works. Let's describe it in math terms. A and B are natural numbers. To calculate their greatest common divisor, calculate the remainder of a divided by b first, and we can use percent to represent the remainder. If the remainder of a over b is 0, b is considered the greatest common divisor, and the calculation ends. Otherwise, we replace a with b and replace b with the remainder of a over b, and repeat the calculation. This is how the division algorithm calculates the greatest common divisor. If we use the algorithm to calculate the greatest common divisor of 18 and 12, see the Python code. We set x and y to 18 and 12 respectively. When y is not equal to 0, we repeatedly calculate the values of x and y until y is equal to 0. After the program ends, we can see that 6 is the greatest common divisor of 18 and 12. This is how the division algorithm presented in Python code. Compared with this algorithm, the enumeration algorithm is simple. and offers intuitive steps throughout the process. But in the division algorithm, each step, for example, x equal y, y equal x% y, xy equal yx% y, is ambiguous. Without knowledge of the algorithm, it's difficult to understand. You'll probably not determine the relationship between the calculation process and the final result, the greatest common divisor. However, this is often the most interesting part of the algorithm. The division algorithm is also called Euclidean algorithm, which was first described in Euclid's Elements. It was also discovered in the Chinese book, The 9 Chapters on the Mathematical Art, with a long history. This algorithm was put onto paper in The Art of Computer Programming, Vol. 2, Semi-Numerical Algorithms, by Donald Knuth, who is a firm believer in the Euclidean algorithm. Knuth claimed it was the granddaddy of all algorithms because it is the oldest non-trivial algorithm that has survived to present day. In 1884, Gabriel Lemay pointed out using the division algorithm to calculate the greatest common divisor requires no more steps than 5 times the number of h digits base 10 of the smaller number, because the computational expense of each step is an h order of magnitude. The calculation times of the division algorithm is the square of h. From this perspective, the algorithm is very fast.